Okay, for another proof by induction, we're gonna prove this. So we have, let's just see what the statement says. It says that the sum of the first n squares, that's the left-hand side, is equal to whatever square you're going up to times one more times two times the number that you're going up to plus one divided by 6. So it's just saying basically that, 1 squared plus 2 squared plus 3 squared plus dot dot dot, I don't know, whatever, 100 squared. Instead of you sitting here and doing this, you can just skip and you can just say it's 100 times 101 plus 201 over 6, and this will be true. That's the theorem that we're proving. Now, to prove this, we prove this by induction on n again. So by induction n, we have the base case when n is 0. We have it sort of trivially, it's trivial because you're going to get 0, 1, and then this is just 1, and then divided by this is equal to 0, and then, of course, the sum of the first 0 squares is 0. But you could also just check for the first one if that doesn't suit you. You could say 1, right? 1 squared is equal to 1 times 2 over 3, and then 6, and you're going to get 1 equals 1. So it works for the base case whether you start with 0 or 1. And then now we say the inductive step. Okay, let it be true. So let this be true up to k. So k squared is equal to k plus 1, 2k plus 1 over 6. And I have a funny feeling we're going to have to do some algebra for k greater than or equal to 0, right? So, and we need to show, right? Let's write down what we need to show. We need to show that, wait, I messed up. It's, no, I'm okay, to k, yeah. This is not n, this is k. I'm using k here. Wait. There we go. Okay. Let's just go through what my mistake was. So this is just that I need to write this to k, and it goes from I, right? So it's just going up to k. So we're assuming that it's true, this statement up to k, and we need to show that it's true if we go to k plus 1. So we need to show that this, we're going to k plus 1, right? And then this is I squared is equal to, and then instead of writing it k, we need to substitute for k plus 1. So then this becomes k plus 2. And then if we're careful, this is going to be 2 times k plus 1 over 6. So we need to show that fact. Okay. This is the inductive step. So we need to show this being true. Right? And again, this is just going to involve a mess of algebra, basically. We need to know that this here, right? What does this mean? All right. K plus 1, I squared. It's equal to 1 squared plus 2 squared plus 3 squared plus all the way dot plus k squared, and then we have up to k plus 1 squared, right? And then we immediately use the inductive hypothesis. We say that this, right, we know is equal to this. So instead of writing all this, we just write that this here is k times k plus 1 over 2k plus 1 over 6 plus k plus 1 squared. Now, we're just going to cheat a little bit. We know what the result we want. We want it to be this, right? So how are we going to make it look like this? We need this. We need to show equality to this and this. and this is going to be an algebra mess. So let's see, how can we do this? You got to just think for a second. Let's just change this to 6 over 6 because this is all over a 6, and then that's fine. Let's see what we have from there. We're going to get this plus 6k plus 1 squared, all of it over 6. And then, okay, I see a k plus 1 and a k plus 1 here that I'm going to try and factor out from the whole thing. So it's going to be k plus 1, big parenthesis, k times 2k plus 1 plus 6 times k plus 1. Right? Because when I distribute back, I get back the original, all over 6. Okay, now let's look at this again. Now let's see what we got. Okay, so I'm imagining that this is the first k plus 1. So really I need to just show that this is the same thing as this. And is that true? So how am I going to get a k plus 1? Oh, well, okay, this is 2k plus 2 plus 1, that's 3. So this is 2k. Okay, so then what can I do here? How can I make this look the same? I need to find a k plus 2 in both of these terms. Okay, well, I'm not sure. So let's just distribute it out. Let's just see what we get. 2k squared plus k plus 6k plus 6. All of it over 6. And then this is k plus 1 times 2k squared plus 7k plus 6 over 6. And this should factor exactly into this. So what is this? Let's see, is this k plus 2? So let's just do this on the side, and let's just make sure that the algebra is right. Because we know the end result. We're sort of, cheating a little bit, but it's okay. K plus 2 times, this becomes 2k plus 3. I argue that this is this. Let's see. So 2k squared plus 3k plus 4k plus 6. And this is that. So then that means that I have my final result. I got that this is k plus 2 times 2k plus 3 over 6, which is exactly this. This, right, is this. If you missed that step. Because if you distribute the 2 and then you combine, you get this. I could rewrite it like this, but I showed that ultimately this whole thing, right, is this, and then I just went down, is this, and then I go here, and then it's this, and then this, and then this, and then this is exactly this, which is what I needed. Because now I showed that if I go to k plus 1, the sum of the first k plus 1 squares is exactly what we needed to, and we're done from here. And this is fine. This is typically messy like this algebra, and you saw how I kind of just figured out that this would factor like this. I try to do it the fastest way possible, but I mean, you just got to put in a little bit more time if you can't figure out the trick to doing this fast. But either way, we did the base case and then we did the inductive step. So by induction, we know, by the principle of mathematical induction, we know that this statement is true.